Hi, I'm Christina, Product Manager for the Google App Engine Search API. In this webinar, we'll provide an introduction to the Search API and show you how to use it in your App Engine application. The Search API lets your application perform Google-like full-text searches over structured data and also supports GeoSearch for location-based searches. It provides a straightforward model for indexing and searching data and displaying the results of search queries. Using the Search API, you can query any data source you choose by creating search documents. You structure data in documents using fields to describe the different types of data the document contains, and then add the document to an index to make it searchable. Once documents are indexed, you can search and index via the Search API's comprehensive query language. When you query, you can specify sort orders on the results, control the presentation and content of the search results with features like snippets, and use cursors and offsets. The Search API can be useful in a range of applications like user review search, searching over blog posts and comments, document discovery, help desk answer retrieval, resume search and recruiting, and product searches in an online store, the example application we'll use in this webinar. In this webinar, we will highlight the features of the Search API and get you started on adding full-text search to your own App Engine applications. We'll start by looking at defining search indexes and building documents, and then move on to querying, sorting, GeoSearch, and finally best practices. For the purposes of this webinar, we'll be using Python, but the flow in Java is quite similar, and Java code snippets can be found at fts-webinar.appspot.com. This webinar assumes that you have familiarity with building an App Engine app in either Java or Python. For more background on App Engine, see our documentation at developers.google.com/appengine. At the end of this presentation, you'll find a resources slide with links to the documentation and other useful sources of information. So now I'll hand it over to Amy, who will demo some of the full-text search features in a sample application and walk you through getting started with the Search API.
Hi, I'm Amy, a Developer Relations Engineer working on the App Engine Search API. We're going to use an example product search application to illustrate some of the features of the Search API. This application shows how you might use full-text search in an e-commerce application. We've indexed two general kinds of content in this app: product information and information about stores, including their geographical location. The application allows a user to find products by searching and sorting the product content, and to use GeoSearch to find stores that carry a given product near to them. So we'll do a short demo first to introduce some of the features covered in the webinar. This is our demo application. It has two example product categories: books and HD TVs. So it's kind of a small store. And it contains indexed product documents and indexed store location information. Okay, so let's do some searches so that you can get a sense of the query language and the Search API features. For the purposes of this demo, we're going to show you the query as is, including the query operators, so you can get a sense of the language. For a real application, you would obscure that from the user. You wouldn't expect them to know the details of the query language. I'm going to start by submitting an empty query. This retrieves all of the documents in the application, sorted by their average rating. Now you can see there are only 12 of them. Now I'm going to filter on books, filter on product category. Okay, so here's an example of filtering on a document field. Now let's sort on price. Okay, so as you can see, we can sort on different aspects of our documents, and you'll note that we have support for pagination. All right, now let's do something a little more interesting. Add a search term: stories. Okay. I'm going to sort my query by relevance. So what this does is it uses a TF by IDF score to sort, term frequency by inverse document frequency. So this is finding documents that are particularly relevant to our search. And notice that we're displaying only a snippet of the description fields, and that the hit on the term stories here is bolded. So let's look just very quickly at the product details of the top 2 hits for that search. And you'll see that this first hit has a number of instances of the word stories in the description, and you'll notice that the description is longer than the original snippet that we were just showing. And if we look at the product details for the second hit here, you'll see that we only have 1 instance of the word stories. So we're sorting the documents by relevance, and we are auto-generating snippets with the hits bolded, and the snippets are showing where the hit was in the long description. All right, now let's look at Boolean operators. So if you just type in some search terms, I will type in stories and novels. This is an implicit AND of these terms. And you'll notice that we don't appear to have any products in our store that use both those terms together. So now let's use the OR operator and do an OR query. And there we get some results. So we have some documents with hits on one or the other of those terms, and you can see again the snippeting is showing where we got the hits and is bolding. You can also restrict a search term to a specific field in an index document, and we'll talk in more detail just a bit later about what we mean by fields. So let's look at the syntax for doing that. One of the fields in our product document is the name field, the product name, and I'm going to search for documents that have the word "the" in the product name. So you can see we're getting some hits, otherwise known as the human condition, for example. And you can combine searches on name fields with other terms like this. So I'm looking for documents that have the word collection somewhere in one of their fields and have the word name in the product. And you can do searches for fields that aren't in all of your documents. So for example, our book products have a publisher field, but our TVs don't. So we can look for something like this. Publisher Penguin. And there's some of our hits for that. The Search API also supports atomic fields, which must be matched exactly. So this means that you can't search for just a substring in that field. You need to search for the whole string to get a hit. And our categories are atomic fields. That's because we want to search exactly on categories. We want to treat them essentially as a token or an enumerable. You can also use numeric comparators. So you do this by using the field name in the expression. So price is one of the field names in our product documents. And so we can do queries like price less than 20. And as before, you can include use of these numeric comparators with other search terms. So now we're looking for all products that have the word novel where price is less than 20. So this demo showed you some of the features and capabilities of the Search API. We'll come back to the example application a little bit later in the webinar to show you a few more concepts. So now let's look at how you can add full-text search capabilities to your own application. We'll start with indexes. Start by looking at what a search index is and how you add content to an index. The Search API operates through an index object, and an index allows you to store content in index documents, retrieve documents using search queries, modify documents, and delete documents. So each index has a name and optionally a namespace. The index name uniquely identifies an index in a given namespace. In your code, you create an index object by specifying the index name. The underlying document index will be created at first write if it does not already exist. So you don't have to explicitly create it yourself. So let's look at what this looks like in your code. First of all, we import the search module. And here, we're creating an index object with name product search 1. The second line here shows what the code would look like if you wanted to specify a namespace that the index was associated with. Next, let's look at how to add searchable content to an index. You do this using documents. Documents hold an index's searchable content. So you add a document to an index, and then once it's indexed, you can query it. A document represents a uniquely identified collection of fields, and it's identified by a unique document ID. Fields are named typed values. So some of the field types that we're using in our example application are text field, number field, date field, and atom field. And all of these are pretty much what you would expect them to be. The documentation provides a lot more information. So I wanted to particularly comment on atom field, which is essentially an enumerable or a token. You only get a hit on an atom field if you search for the entire string, not a substring. So let's look at the structure of the product documents in our example application. We've got two different categories of products, books and televisions, and each product document always includes certain core fields, which this figure is indicating by these boxes here. So some of these core fields are product ID, name, description, category, price, date, and the rating of the product. Then the televisions have some additional fields, such as TV type and brand, and the books have some additional fields, such as publisher. And so we're imposing this structure, the semantics, at the application level. So in our example application, product documents always include the same core fields. All televisions always have the same additional fields, and so on. But documents themselves in the Search API do not intrinsically have kinds in the sense of data store entities. You impose semantics on these documents at the application level. So you can use namespaces and indexes as well as field values to organize your documents. In the example application, there are two indexes. All of the product documents are in one index, and another index which holds information about store locations we'll talk about a little bit later in the webinar. So let's take a look at how we build a product document. The first thing that we do is define the fields, and then we create the documents from the fields. So in our example application, we're using text fields, atom fields, number fields, and date field types for product documents. And particular, worth commenting that we're using atom fields for the product category names. This means that if we search on the category field, we need to use the exact category name string, not a substring, to get a match. So atom fields can be particularly useful for things like categories, where exact matches are expected and where we don't want to match on substrings. And text fields can be better for things like titles or descriptions. So given the fields, we can create a document object. For each product document, we'll set its document ID to be the known, predefined, unique ID of that product. And if we did not specify the document ID, one would be auto-generated for us when we add the document to the index. And so this is what the code looks like. We have built the product fields. We're creating a document object using those fields, using that content. And in this case, because we have unique product IDs for each of our products, we're setting the document ID to be that product ID. Okay, so we've looked at how to create documents from fields that hold the document content, and now we can add them to an index. And let's look at how to do this. This allows the documents to be searched using the Search API's query language and query options. So here, we've created our document. Now we're going to use the add method of the index object here to add the document. And the results of doing the add are an iterable. In this case, we've called it add result. And you can extract the assigned documents IDs from that iterable, as we show here, with the results returned. So if you didn't assign a document ID to a document, then this is how you could obtain the document ID that was auto-generated. And if you did assign a document ID, like we showed here, then what would be returned would be that same ID. And so when you do a document add to an index, be sure to catch any exceptions that result. Here we're catching search.error, which is a general Search API exception. All right, so let's just take a quick look again at a product detail page from the example application. And this is showing, just for demonstration purposes, the raw field names that we're using for this document. And obviously you would not want to expose this in a real application. And so you can see that these are all of the fields that we're using in our documents, and you can see their content. And you can add documents one at a time, or you can add a list of documents in batch. And that is more efficient if you add them in batch. So far we've talked about how to build indexes and build documents and add them to the indexes to get queryable content. So next, Jed is going to talk about how to search over our indexes.
Hi, I'm Jed, a software engineer working on the App Engine Search API. By adding documents to an index, we have made the document content searchable. So now we can perform full-text search queries over the documents in the index. There are two ways to submit a search query. Most simply, you can pass a query string to the index search method, or you can create a search query object and pass that to the search method. Construction of a query object allows you to specify query, sort, and result presentation options for your search. First, we'll look at how to construct simple queries using both approaches. Then later, we'll look at how to perform more complex queries using the query object. A query string can be any string that can be parsed by the Search API's query language. See the Search API's documentation for a detailed description of the query language. The query string should be a Unicode string. The example looks for products that contain the terms writings and collection. The query string is passed into the index object search method. It's here. And then later we'll see how to process the search results that are returned. A search query object gives you more control over your query options than does just a query string. Here we first construct a query options object. Its argument specifies that the query should return a limited number of results. Then we construct the query object using the query string and the query options object. We then pass a query object into the search method. Once you've submitted a query, search results are returned to the application in a search results object, which includes a number of results found, the documents returned. The number of results returned is the length of the results property. The number found property is set to the number of hits found in the search. The returned documents are accessed by iterating on the search results object. You can then access the properties of the document, such as doc ID and fields. As we have discussed, you can submit a search query using a simple string or alternatively, a query object. The query class constructor takes as arguments a query string and query options object. The query options object allows you to configure a wide range of options to fine-tune your search. Let's take a look at one of the query options configurations used in the example product search application. Here we are setting a query offset, a limit, and some sort options, and a list of snippeted fields, and a list of returned fields. Let's take a look at what each of these properties do. To control the number of results that a query returns, use the limit parameter of the query options constructor. In the example product search application, we use limit to return at most 3 results per page. We also use the offset parameter. The offset indicates the number of matched documents to skip when returning results. The limit and offset parameters provide support for pagination in the product search application. To implement pagination, we also need to know how many results were returned from this query and how many matches were found in total. As we saw earlier, we can get the information from the returned search results object. The use of snippeted fields allows you to return an abbreviated snippet of a field instead of its full content. And if your search query has a match on the snippeted field, then the snippet will include the fragment of the field in which the hit occurred and will highlight in bold the search terms in that fragment. In the product search application, a search query returns 3 hits in the document's description fields because we requested that description to be snippeted. The snippet expressions in the results have stories highlighted. You specify the snippeting that occurred by specifying fields to snippet. In the product search application, we request snippeting of the description field. Then, when you're processing your query, you can access the generated snippets from a returned document's expressions property. The expressions property holds a list of computed fields which are the result of expressions requested in the query. This includes snippeted fields. So here we're grabbing the snippet generated for the description field of a document returned by the search results. The returned expression property allows you to define computed fields based on your document fields that are returned as part of the scored document in the search results. As a simple example, suppose that we want to calculate prices including sales tax for our products. Suppose the sales tax is 8%. We create a search field expression with the name adjusted price, whose value is price times 1.08. After including a returned expressions list in our query options object, we can access that computed field in the documents returned from a search query via the expressions property, like we did in the generated description for field snippets. We've now looked at some ways to define more exactly the documents to be returned from a search, but we haven't yet discussed how to order the query results. You can sort on a field value as well as expressions that include the field value. Sorts can be multidimensional, sorting first on one field expression, then on another, and so on. In addition, you can sort on a score based on the document's term frequency by inverse document frequency ranking, or you can make use of that score in a more complex ranking expression. Let's take a look at these query sorting features now. The SortOptions class provides the basis for defining query result sort orders. A SortOptions object, once defined, is used as the SortOptions parameter of a query options constructor. A SortOptions object can be configured in a number of different ways. Let's take a look first at the MatchScorer class. It is used to sort documents in descending order, using a score based on term frequency by inverted document frequency. This sort is used by the example app when the user selects relevance from the query sort menu in the UI. To use match scoring, a MatchScorer object is passed as the MatchScorer parameter of the SortOptions constructor. You can also pass the SortOptions constructor an expressions argument, which is an iterable of sort expression objects. This lets you perform a multi-dimensional sort based on the document field values. Let's take a look at how we're using SortOptions in the example application. We define a sort expression object for each product document field that we plan to use in the UI as an available sort. For example, here are the sort expression objects for the price, product name, and average rating fields. For all of these definitions, the expression parameter here is simply the field name. As we'll see shortly, the expression can be more complex. We define the sort direction for each such field. For example, we're sorting price and product name in ascending order. With average rating, we want to sort in descending order. Since this is the default sort direction, we don't need to specify it. We're also defining a default value, which is used if a given document doesn't include the field in the expression. For a string-based field like product name, the default value must be a string. For numeric fields, it must be numeric. We create a SortOptions object with the expressions parameter set to a list of these sort expressions. Then, as before, we pass the SortOptions object to the query options constructor. The expression property in the sort expression object can be more than just a field name. For example, we can access the document score in the sort expressions. This is done using the special construct _score. The sort expression sorts on the value of the average rating field plus the document score. If you access _score in a sort expression, your SortOptions object should include a scorer. So here we've included the MatchScorer object. And now my colleague Bo is going to talk about GeoSearch and best practices using the Search API.
Hi, I'm Bo. I'm a software engineer on App Engine working on the Search API. I'll take you through location-based search. Location queries are what allows you to find all nearby restaurants or all nearby stream updates. In order to execute a location-based query, we need to have three pieces of information. First, we need the point from which we're measuring the distance. We also need to have some sort of distance, such as 10 kilometers or 10 miles. Both of these are usually supplied by the user. The last piece of information is the set of points to which the distance is being measured. These need to be set on documents, which represent some real-life objects, in our case, stores. Okay, first, let us look at the location search in the application. We found a product, a book, Runaway, and we want to purchase it. So we initially enter 20 kilometers radius and try to look for all the stores. This finds some stores in Mountain View, some stores in Sunnyvale and San Jose. We can widen our search, make it 40 kilometers. This time we find pretty much all the stores in the Bay Area. And since it's a particularly nice day, we might drive driving even further. So now we are looking for everything within 100 kilometers, and it finds one store in Carmel Valley. So let's look how to include this information in a document. A location is defined by a GeoPoint class, which stores latitude and longitude. The latitude specifies the angular distance in degrees from the equator, and the longitude specifies the angular distance, again, in degrees from a prime meridian. For example, the location of Opera House in Sydney is defined by a GeoPoint minus 33.857, which is the south, and 151.215 west. In order to store a GeoPoint in a document, you need to add the GeoField with a GeoPoint set at its value. Once the documents are constructed and added to the index, we are ready to run the search query against them. A GeoSearch query uses the distance function, which takes a field name and a GeoPoint. The field name is the name of a field that you are searching on. The GeoPoint identifies the location from which you're searching. We compare the value returned by a distance function with the distance specified by the users. If you were in Sydney Opera House, say listening to Puccini's Tosca, and experienced a desire to locate the stores within 4.5 kilometers, you would use the following query. You would enter distance from store location from GeoPoint that identifies the Sydney Opera House is less than 4,500. The distance is measured in meters. Running the query against the index would return all documents for which store location field records a point that is less than 4,500 meters away from Sydney Opera House. Getting all stores within a given distance is nice, but what would be even better is if we could sort them by how far we need to walk or drive. This can be done by adding a sort expression. Again, assume that the user is browsing store location from Sydney Opera House. The query that finds the stores within 4.5 kilometers and sorts them by the distance from a user would look as follows. The query string remains the same. Distance from a store location to a GeoPoint is less than 4,500. What we add is the sorting expression, which asks to sort by distance, again from the same point based on store location. We sort in ascending order, which guarantees that the stores that are closest to us are returned first. This concludes our quick overview of the location-based searches. Let me talk about some best practices for Search API. We did not provide a separate update document operation. The semantic of an index is such that adding a document with an existing ID simply updates it. But it also means that you should manage your own document IDs if you plan updating documents. Managing your own IDs is also a good idea if your documents represent some external objects. For example, if your document is a searchable representation of a data store entity, you could set the ID to the key of the entity. When you search, you can ask for the index to only return document IDs, and then convert them back to the entity keys and retrieve all matching entities. With regard to index name, it is more efficient to have one index per user than one large index and store owner attribute with each document. The only time you could consider having one large index is when you need to find all documents, regardless of which user owns it. Each document has a rank attribute. If not set, it is assigned the time the document was added to the index. The documents are pre-sorted on rank both in ascending and descending order. If you do not specify the sorting criteria, we simply return documents in descending order of their rank. This is the result of having the freshest documents first. If you have one simple order, say rating, in which documents should always be returned, you should assign rank value yourself. This significantly speeds up your search queries. If you plan to insert or delete a large number of documents, please use the task queue. This allows you to control the rate of insertion and do retries on documents that did not index due to transient errors. Add-on fields is our version of enum values. Add-on fields must be shorter than 500 characters, however they are not tokenized. As a result, add-on field full space bar is not the same as add-on field full comma bar. You can even use them to do your own tokenization by inserting repeated add-on fields. However, please remember that this comes at a price. And now off to Christina for some closing remarks.
So that about sums it up for our webinar. Thanks for watching. To learn more about the App Engine Search API, check out our documentation and sample application, and ask any questions on Stack Overflow with the Google-App-Engine tag. Happy coding!